on this paper. That is Danny Merkx. This is part of his PhD research. Unfortunately, Danny was not able to present it himself, so I'm taking over from him. For the Q&A, this means that if you have particularly technical questions, I might not be able to answer them because Danny knows a lot more about the details of this work than I do. Artificial intelligence is nowadays mostly based on machine learning. And these machine learning models are trained on large databases. These are getting larger and larger. Language models, for example, are trained on maybe 500 billion words nowadays. That is a lot of words. That is more than people experience in their entire lifetime. The reason to use such large training sets is, of course, because it makes the models more successful. At least it improves the performance on the training task, the task that the model is trained to perform. In practice, we are not always interested in the training task, but we want the model to then be able to do other things as well. This is when we're talking about transfer learning. So we want the training task to transfer to another and maybe more useful task. Now, children learn language from relatively small amounts of data compared to what these large language models see. And also children, of course, don't learn language from spoken text. They learn it from speech or maybe sign, and from how that language input is associated with what the children experience in other modalities. So that is what they see, what they hear, what they feel, what they smell, etc. If we want to have a model that is a bit more realistic, in the sense of that learns language more like a human does, it needs to be trained on smaller amounts of data, and it needs to be trained on speech in association paired with another modality. This is why we use visually grounded speech models. These are multimodal models that receive both images and spoken captions describing the image, and they have to learn to associate these. These models too are trained on ever-larging datasets. A few years ago, when this kind of work was first done, the standard dataset was Flickr 8K with 40,000 captions. More recently, Places Audio has 400,000 captions, so 10 times as large, and even a higher increase in the number of images. And the most recent work that we're aware of, Spoken Cocoa, has over 600,000 spoken captions. When it comes to VGS models, too, the training task is often not of interest, but people are interested in what these models can do when they have been trained. For example, can they discover lexical units such as words? Can they spot keywords? And what have they learned about the meaning of sentences? And it is this last transfer learning task that's also the topic of this talk. So what we're going to do is take a VGS model and look at the sentence semantics that it develops and how that varies with the training database. Now here is a very simple sketch of the model we use. We start with a pre-trained, standard, easily available neural network for image recognition called ResNet. This has already been trained on many images. And we have on the other side a speech processing network that we have developed ourselves, but it's also pretty standard, where we take the captions that describe the images, turn them into speech, and feed them through this neural network. So both parts of this network, in the end, output a vector representation called an embedding of either the image or of the spoken caption. And the goal of the model is to make the image embedding as similar as possible to the caption embedding, and vice versa, at least for the images and the captions that belong together. So the datasets we use are the three datasets that I just mentioned, Flickr 8K, Places Audio, and Spoken Cocoa. Here I added a column indicating the number of captions per image, which clearly varies, and that will become important later in this talk, so please keep that in mind. Of all these captions, 1,000 for each of the three datasets were put aside for later testing. So the actual training dataset is a little bit smaller than this. Like I said, the objective of the model, the training objective, is to maximize the similarity between the embeddings of images and captions that match. So captions that describe the image. If this was the only objective, it would be a bit too easy because the model could just make all the embeddings identical to each other. So all the captions and all the images would have the same embedding, and then it would have maximized the similarity. So it also needs to minimize the similarity between pairs that are mismatched, so captions that do not belong to the image, and vice versa. If you like to see the precise loss function, this is it. So here we have pairs of captions and images, denoted by C and I. So these are two of such pairs from a certain training batch, where they match, so the caption and the image belong together in a pair. Then this similarity, this cosine is the similarity measure here. So this needs to be maximized. The cosine between the different non-matching images and captions needs to be minimized. So all in all, when that works, then the loss is as low as possible. Does it work? Well, we then tested using these 1000 image caption pairs that were put aside. And for each of the captions that we then feed it from this test set, the model will output a ranking of 1000 images, where the number 1 is, according to the model, the best matching image, 1000 the worst matching, and vice versa. We can also give it one of the 1000 test images, and it will output a ranking of captions. So here you see the median rank of the actual output, the median rank of the target output, so the correct output in the 1000 list. So this 12 means that in the median, the 12th item in this ranking is given the caption is the correct image, and here the 7th item given the image is the correct caption. So lower is better, it's higher in the ranking. What we have here is the recall, that's a percentage of targets outputs that are in the top n of the output. And as you can see, so larger is of course better. So larger recall, larger percentage means more. For more of the outputs, the actual target is in the top n. So larger training databases lead to better results. Higher recall percentage than the Flickr 8K here, and lower median rank, both for going from caption to the image as from going from image to the caption. Again, larger databases results in higher performance on the training task. So how about the transfer task? What we're interested in is the meaning of sentences. Do people score similarities, semantic similarities between sentences similarly to what the model does? So for this we take the so-called semantic textual similarity database, which is 12,500 sentence pairs that have been annotated by human judgments of how semantically similar these sentences are. The sentences come from many different sources like news, posts, tweets, but also image descriptions of the kind that the models are trained on. Now the STS database has written language. Of course we have a speech model, so the first thing we needed to do was create a spoken STS model. And we did this by feeding the 12,500 written sentences into a speech synthesizer, where we selected 6 UK English voices, 3 male and 3 female, and a small sample of 5% of these sentences was also recorded by human speakers, again with a North American accent. Now, does it work? Do the caption embeddings mirror human semantic similarity ratings? So we look at the cosine similarities between the pairs of STS caption embeddings, and we compare these to the human similarity ratings for the same pairs. And then we see that the correlation between these two sets is actually quite high, so up to 0.6. So indeed, sentences that are rated as highly similar by humans have caption embeddings that are close together. So this here is for the entire data set. If we just look at the 5% of sentences that we had recorded by human speakers, the percentage is, the correlation is a bit lower. So apparently the model has more difficulty with natural speech than with synthesized speech, which is interesting because it was actually trained on natural speech. If you take the same 5% sample and look at the synthesized speech for these, then it does just as well as overall. So the sample was really a proper random sample. But more importantly is the comparison between the training datasets, where we see that Flickr actually does a bit better than the other ones, even though it is the smallest, by far the smallest training database. Like I said, the STS data comes from different sources. It's interesting to look just at the image descriptions, because here we see that, first of all, the correlations are much better, which is not surprising because this is the kind of data the model was trained on. But also this is exactly where the larger databases actually outperform the smaller one, in particular in this three. So these are two different sets of image descriptions from two different years. So the largest database actually only does best when looking at image descriptions. Also, by the way, video descriptions. So why doesn't this very large places audio database perform so badly? Well, be reminded that Spoken Cocoa and Flickr 8K have 5 captions for each image, but Places Audio only has 1. These 5 captions are most likely paraphrases from each other. There's not so many different things you can say about these images. If you see an image of puppies playing in the grass, you might call them doggies. You might say field instead of grass, but these all will be paraphrases. And of course, for learning what the sentence means, it can be very useful to have different sentences describing the same image, because this is a good learning signal for learning these sentences apparently mean the same thing, so they are paraphrases. So is this indeed what goes on? Does this help performance? So to test this, we took 30,000 sentences from the Spoken Cocoa database and then varied the number of captions for each image between 1 and 5. And what do we see? Having more captions indeed slightly increases the correlation between human judgments of semantic similarity and the cosines between the sentence pairs according to the VGS model. We also tested this in a regression analysis where the human judgments have to be predicted by the model cosines, and here we see from the AIC values that indeed having only 1 caption results in a substantially worse fit of the regression model than having 5 captions. What is noteworthy is that when the number of captions per image increases, the number of images, different images in the training dataset decreases. So these models that were trained on more captions per image have actually seen a smaller variety of images, which would usually be detrimental to performance. So in spite of that, it actually does a little bit better in the training, the transfer task. So to conclude, our model actually does develop representations that somehow mirrors human judgment of semantic similarity. We also looked at whether it really helps to have always larger training databases. Yes, it does for the training task, but it does not for the transfer task. If you want to have a model that captures human ratings of semantic similarity, the smaller database, the Flickr 8K trained model, actually does better. When it comes to the image or video description subset of the STS dataset, there the larger databases actually did result in better performance. So perhaps they are just over-specializing to this very limited domain of training, which is image descriptions. All in all, it turns out the small dataset, Flickr 8K, can still be useful. These larger datasets are, of course, expensive to collect, hard to train a model on. So if you need semantic similarity ratings from your model, better to use the smaller one. Now, having multiple captions per image turns out to be useful as a learning signal. So all in all, there are more properties that are useful in a training database than just having the largest possible database. Thank you for your attention.
Thank you for the presentation. Do we have any questions in the room? Before you presented the issue on the amount of sentence, the captions in Flickr, I was thinking that there may be some domain shift or something like that between the datasets and the second corpus. So is this also a possible contribution, or they are all essentially about the same thing and it's just the size effect?
Well, they're all image descriptions. So people just saying what they see in an image, in that sense, very similar. But it's not the case that the smaller dataset is part of the larger dataset. So they are distinct sets. As far as I know, don't think there's any like fundamental systematic difference though.
Mm-hmm. Thank you. Do we have any more questions? Well, if not, I guess we can thank the speaker, and there is. Oh, excuse me. Yes, the mic is there. We actually do have a question.
Hello. My question was, don't you think that maybe getting directly to semantic similarity as a transfer task is maybe a far reach? Maybe you can try it, as you were interested by babies learning visually grounded speech, like maybe easier tasks, and see whether actually adding the visual thing helps for easier tasks like, I don't know, words recognition or words discovery or things like that.
Yeah, actually that's what we're working on now. Not so much looking at infant data, but looking at human representations of lexical semantics as measured by, for example, semantic priming, to see whether adding the visual input helps in that case. Yeah. And there's some earlier work by others that show that might indeed be true.
Okay, thank you.
Are there any more questions that I have missed? Okay, if not, I'm double checking. Let's thank the speaker.